Rod from VMN here, home of the spaceship plasma cutter. I wanted to talk to you a little bit about the sophisticated high definition hole processing mode that exists in monochrome plasma. So I wanted to start here with a simple hole, and we want to start at, I'll get a black pen, we want to start cutting at 12 o'clock just to make the math simpler, and we always want to pierce at the centre of the hole to give the maximum amount of room for the slag to fall out. So then we want to start our lead in from here, and we're going to lead in to a specific point, and then we're going to do an arc, which I'm not very good at drawing, all the way around here as the lead in to the beginning of the hole. Now this gives us a nice tangential entry point that maximises cut quantity. So the next thing is that from our database we know for this specific hole on this specific material using this specific cut chart that we're going to cut this hole at what we're going to call speed 1 all around here to this point here, and then we're going to turn the torch off before we get to 12 o'clock. So we're going to continue here at speed 2, and we're going to turn the torch off, and we're going to continue here like this, and then we're going to do a little bit of an overburn. So if we have a look at that, we've got speed 1 here, speed 2 here, off here, and overburn here. So that should give us the maximum hole quantity if we know what these values are. So how do we know what those values are? Well, we keep that in a database for that specific cutting process on that material at this amperage. So we might have, say, 2 of these settings here, and we're going to define these based in terms of a ratio of the thickness, which will allow us to use it for other materials where we don't have an exact match. So if we said this was 10 millimeters material, and this was 30 millimeter diameter hole, then this we're going to say as a thickness of that ratio is 3 to 1. So the first setting we might have in our database is 3:1, and then we might have 5:1, and we may have 8:1, and we may have more entries down here if we need to. So within this we will have these entries here for speed 1, speed 2, lead in, arc radius and length, and distance before off, and the overburn, over travel. So okay, so the post processor, when it goes through here, it's going to throw out all of the code that it has for holes in the process, and it's going to generate them itself according to these parameters. So we're going to take this 30 mil hole, 10 millimeter thickness, we'll go to the 3 to 1 entry, and we'll format that so it looks like that. So if it was a 50 millimeter hole, it'd be 5 to 1, so we would use this entry here. But what if we had a 25 millimeter hole? Well, what we're going to do here is extrapolate these values so that we're going to pick these values based on the difference between these two. So 25 millimeters is exactly in the middle, but if it was 20 millimeter, if it was, I've got that a bit wrong, but if this was in the middle here at, say, 40 millimeters, it's exactly in the middle. But if it was 42 millimeters, it'd be here somewhere, so we actually extrapolate that value. So in this way we can create a very powerful hole technology in a high definition plasma cutter, say from the likes of someone like Hypertherm. They will have all the smarts built into their CAM system, which I think they call ProNest. But LinuxCNC doesn't have a CAM system. It doesn't have a post processor. So the way that we do this is we apply all these changes within what we call the filter. So within LinuxCNC we can filter a G-code program and modify it. So we modify it, we strip out the existing hole cutting data or holes, the paths, and we replace it with the ones that we generated from this data-driven approach. So if then you have what we're providing here is a framework for anybody to use an open source system with a high definition plasma cutter, and but also that we're able to bring these features down to the cheaper air plasma cutters that most people use on home design tables. So that's the end of our little presentation. So thanks for listening.